Well, welcome everybody. I'm Scott Robson, and I am thrilled to be presenting to you from San Mateo, California. And today I'd like to talk to you a little bit about exoplanets. So what is an exoplanet? Well, as the subtitle of my presentation might suggest, an exoplanet is a planet beyond our solar system. So it's a shortening of extrasolar planet. So these are the planets within our solar system, our nearest neighbors. And really, we're only beginning to dip our toes into understanding these planets within our own solar system. That said, it's really only the beginning. So here's our most current map of the Milky Way galaxy, our own home galaxy. It's thought that beyond our solar system, there are many, many stars, some 300 or 400 billion stars. If our star, which is fairly unremarkable, it's great, don't get me wrong, but fairly unremarkable by galactic standards, has so many planets, 8 for the record, might other stars host worlds of their own? That's the question. And here's just a different view. This is kind of a compressed view of our night sky as seen from Earth. Think of it as a map of the visible galaxy in terms of how you look at it from the ground. So that bright curve to the center left, you'll see that. That is the center of our galaxy. So a little bit of a brightening and a bulge there. So let me annotate this map for you. Every circle that you see represents a confirmed exoplanet discovery. The different colors represent different detection methods. We'll get into those later. And you'll also note the dense concentration towards the top left of the field and a smaller blue cluster near the galactic center. Those will be important later. But for now, just kind of marvel at all the circles and know that each one of those is a confirmed exoplanet. So the answer is yes. There are lots of planets outside of our solar system. Zooming back out above the galaxy, here's an artist's impression of our current exoplanet search efforts. So you see that kind of red ray going towards the top? That's where most of these purplish circles are concentrated. So that's where the Kepler space mission was focused. And it's kind of our MVP in terms of exoplanetary search efforts right now, although it has recently retired. My point being, we've already found lots of exoplanets. As a matter of fact, we've found 4,082 confirmed exoplanets as of today. And if you look back at this galaxy map for just a second, we're barely scratching the surface. So it's a really exciting time for astronomy because we're really just in the last few years being able to search for these reliably. So let's talk about what we found. So of the 4,082 confirmed exoplanets, by the way, I had to correct that number right before this presentation because it was a different number yesterday. So our search efforts are ongoing. We have found 1,375 Neptune-like planets, 1,271 gas giant planets, 1,269 what we call super Earths. I'll talk about that later. 161 terrestrial planets, more or less like Earth, and 6 planets that we can't really tell exactly what they are for various reasons. So let's go through these different types of worlds that we found. So terrestrial exoplanets are basically rocky planets, much like Earth, Venus, Mars, or Mercury. So they have solid surfaces and atmospheres. Now, when I say terrestrial, I think a lot of our hope is that it'll be very Earth-like. And some of them may be, but the fact is we don't yet know. These stars are incredibly far away, and the planets that orbit them are very, very, very small by comparison. So we don't have a ton of information, but by using indirect observation methods, which I'll get into later, we can learn a bit about some of these worlds. And I've got some interesting favorites that I've picked out to talk about later. But we have found 161 of these. Why so few, you ask? Well, it's really hard to see something the size of Earth 12,000 light years away. So I'm confident, and this is just an educated guess, I'm confident that we will see more and more terrestrial exoplanets in the next decade or so as our observation capacities increase. So I mentioned super Earths. These are where things start to get a little bit fuzzy. So it's pretty straightforward to measure the mass of an exoplanet based on its effect on surrounding objects. So we know these are larger than Earth. An exoplanet is defined as a super Earth when it's heavier than Earth, but not more than 10 times heavier than Earth. More massive, I should say. So these worlds are large. They may, depending on their density, be kind of just larger versions of Earth, like this artist's illustration suggests, terrestrial planets with rocky, solid surfaces, or they could be more oceanic, depending on the amount of water they contain. And some may blur that line where they're perhaps considered more of a mini Neptune. So you might have noted a few slides back that Neptune-like planets were the most common exoplanets we had discovered, and that's true. Most of the planets, well, not most, the most common category of planet we've discovered is Neptune-like. So these are planets between 10 and 50 times the size of Earth. For reference, Neptune is about 17 Earth masses. Now, while we call these Neptune-like, we don't actually know the composition of most of these worlds. Some of them may be very, very, very small gas giant planets. Some could be ice giants, similar to Neptune or Uranus, or others could be very large rocky worlds, kind of similar to Earth, or just massive Marses. But we have found a lot of these. And the majority of them that we found are fairly close to their suns relative to our own Neptune-like planets. The reason for this, of course, is it's easier to detect a planet close to a neighboring star than it is distantly from one. And I'll get into reasons for that shortly. Meanwhile, continuing our survey of types of exoplanets, there are the gas giant exoplanets, or Jovian exoplanets. These are big, anywhere between 50 and 5,000 times the size of the mass of Earth. Jupiter, for reference, is about 318 Earth masses. So these are large solar system defining planets. Our giant planets are all found in the outer solar system, which is probably very fortunate for us. But we have discovered some that orbit much, much closer to their stars. So the artist's illustration on the right is an illustration of what's called a hot Jupiter. So these are Jovian planets that are basically right on top of their stars. They're much, much, much closer to their stars than Mercury is in our solar system. So extremely hot, blistering worlds. And I'll talk about my favorite of these in a little bit. But that's not all. We've also found other planets that kind of defy our own understanding based on what we've seen in our solar system. So while Jupiter's king of our solar system, there are planets in our galaxy that are tremendously more massive. These are known as super Jupiters. Even these very massive worlds, which could be, say, 10 times the mass of Jupiter, which is mind-boggling in itself, aren't much larger than Jupiter in terms of diameter. So gravity tends to compact them even if they become more massive. Now, there are some that are what we call puffy, which seems like a kind of planet-shaming term, but they're larger than Jupiter in terms of diameter because of other circumstances, such as extreme heat from a star, which kind of causes them to expand due to physics. Now, there are some other massive bodies the magic number seems to be larger than 13 times the mass of Jupiter, that start to blur the line between planet and star. And we call these brown dwarfs. The image on the left is actually a direct image of a binary brown dwarf pair called Lumen 16. And these are the nearest known brown dwarfs. They're only 6.5 light years away, so very, very close to our solar system in terms of the scale of the galaxy. Now, these objects aren't actually brown. We kind of think they would be more of a magenta or gentle glowing red, kind of like the artist's conception on the right, but they are incredibly massive, and some may have their own planetary systems. They generate their own heat, but aren't quite large enough to be a star in their own right. They can't sustain nuclear fusion the way a main sequence star like ours will. They are curious objects, and now that we've discovered Lumen 16, we can study it more closely. These are relatively new objects to our understanding. So how do we discover all of these phenomenal exoplanets? Well, there are many methods, but the four main methods are the ones I'll cover here. So the first is the transit method. Just like transits in our own solar system of Mercury or Venus, this is essentially when a planet passes between us and the star we're observing, causing a dip in that star's light curve. With shorter orbiting, with planets with a shorter orbital period, this allows us to get a very predictable sense of when they're crossing and allows us to determine the distance to that star, between that star and that planet, rather. So this is by far the most popular or successful method. This is the method the Kepler mission used, very accurately tracing the dips in light as a planet crosses the limb of the star. So 76.6% of exoplanets have been discovered using the transit method. Very successful. Next is the radial velocity or Doppler wobble. I kind of prefer Doppler wobble, but it doesn't sound as professional, so I used radial velocity here. 19.2% of exoplanets have been discovered using this method. And essentially this looks at the light of a given star and watches it very carefully for these wobbles. Just like, when you're driving and you hear the shift in sound as a vehicle passes you, it kind of goes, well, light does that too. So when a star is moving towards us, its light is slightly blue shifted, so it gets compressed slightly, the wavelength does. When it's moving away from us, it's slightly red shifted, so the waves are elongated slightly. And that is a very detectable phenomenon, especially when it's caused in predictable patterns by an unseen planet. We can use this to infer the existence of one or more planets. So very, very successful method as well. There are a couple of other interesting methods that we've been able to use. One is called Gravitational Microlensing. So this one's a little more complicated, but essentially it allows us to observe extremely distant objects using the gravity of an object of incredible mass. So in this diagram, it kind of explains it pretty well. So that yellow dot all the way to the right, imagine that's a distant star. Its light is going to move out in a straight line away from it. Its light will eventually be bent by a kind of interposing object, in this case, a star system or other massive object, allowing us to see objects behind it under certain circumstances. This allows for short-term observations of things. Some research teams have reported finding free-floating rogue planets in adjacent galaxies, so millions of light years away using this method. Now, only 2% of accounted exoplanets have been discovered using the microlensing method, but it holds a lot of promise for real deep kind of observations. Sorry, my headphone popped out here. 1 second. And the final method we'll talk about is direct imaging. Only 1% of exoplanets have been discovered this way, but this is really exciting. It allows us to directly image planets around other stars. So the trick is we need to block out the light of the star we're observing in order to really see the much dimmer, relatively speaking, planets. That said, we've started being able to do this, and kind of modern machine learning methods are allowing us to do it with much greater efficiency. So I wouldn't be surprised if in the future we're not only able to really resolve smaller and smaller planets this way, and closer to their stars, but even resolve some surface features. So using direct imaging, we've been able to see surface features on the star Betelgeuse, for instance. Now, of course, that's a massive star, but as our technology improves, we will probably be able to get closer and closer. So one topic that inevitably comes up when discussing exoplanets: could there be life, or could these places be habitable? Well, let's talk about what that would look like. So there's a concept called a Goldilocks zone, or a habitable zone around most stars. Well, I'm trying to think of stars that wouldn't, but in any case, it's kind of common sense that the hotter a star, the further out its habitable zone will be. So in our solar system, kind of represented by that center diagram there, our habitable zone kind of just barely grazes Venus. Earth is pretty much smack dab in the middle of it, and then Mars is kind of on that extreme outer edge of arguable habitability. So just because something is in a star's habitable zone does not mean it is in fact habitable. Conversely, cooler stars, you can get much closer to those stars and still be in an area where water can be liquid without evaporating or vaporizing or freezing. On the other hand, as we'll discuss later, that brings its own challenges if you're that close to a star. And hotter stars tend to be shorter lived, so, would chance have an opportunity to evolve and arise in these places. That said, we have found a number of worlds that are pretty promising in terms of their ability to harbor what we know of as the ingredients for life. So liquid water, tolerable radiation levels, temperature that is sustainable. So looking at this, where Earth again is kind of smack dab in the center, we found a few exoplanets that look like they could theoretically, given ideal conditions like chemistry and things like that, potentially have what we would think of as the ingredients for habitability. Expect this list to grow tremendously as time goes on. So this is really exciting work being done. It's a fascinating time to be looking at planets outside our solar system. So now I'd like to talk about some of my favorite exoplanets that I've studied, that you won't find anything quite like them in our solar system. So first, let's talk about this planet. It's got a kind of dry designation. It is called PSR B1620-26b, but informally it's known as Methuselah, or the Genesis planet, due to its extreme age. It is nearly 13 billion years old. So it's seen some serious stuff. by comparison, our sun is only 4.6 billion years old. So this star, which orbits a pulsar and a white dwarf, has been around since some of the earliest days in the universe. And it is hanging out a bit larger than Jupiter, and it takes about 100 years to orbit its binary star pair. Now, it's thought that the pulsar was once kind of more of a main sequence star that went through a red giant phase, but it's pretty provocative to think about what this star might have seen in its 13 billion years. Next, we have what I like to call Saturn on steroids. It is known as J1407. It's either a giant planet or a low-mass brown dwarf with a giant ring system, and I mean giant. The rings are estimated to be about 90 million kilometers across. So just to put that in perspective, that is 2/3 of the way from Earth to the sun. If Saturn had rings like that, they'd be many times larger than the full moon in our night sky, or as you see here in this artist's conception, our daytime sky. So if Saturn had these rings, that's what it would look like. Really spectacular that there is a world out there with rings like that. We don't know if these are stable. Based on our best estimates, those rings have about the combined mass of Earth. And it looks like some of those gaps in the ring, which you can see, are probably filled with moons of some kind that are kind of shepherding the rings. So pretty remarkable, but we discovered these rings based on dips in that star's light curve as the rings kind of passed. Really extraordinary work. So next up on our list is Kepler 70b, burnt to a cinder. So it is incredibly close to its parent star and has one of the shortest recorded orbital periods. So it has a year that is only 5.76 hours long. So it's moving very, very fast. It is very close to its star, and it has a surface temperature of, only 8,000 degrees Celsius. So it's not where you'd want to go on a vacation. It's presumably also heavily irradiated. So its presence that close to its sun kind of defies conventional methods or conventional understandings of planet formation. So here's our best guess of what happened. Once upon a time, Kepler 70 may have been a sun-like star, so a G-type star, that went through a red giant phase. It's thought that Kepler 70b, now the innermost planet in that solar system, was a gas giant planet that was consumed by the red giant phase. So red giants can expand well past the orbit of Saturn. So they can become massive. All of that material might not have incinerated Kepler 70b, but it would have slowed its orbit down, and it would have probably burned off most of its gaseous atmosphere, leaving the dense, rocky, metallic core of a giant planet in very close proximity to what is now Kepler 70, a hot B-type subdwarf star. So that, is a terrifying thought to me. Just like a giant planet like Jupiter getting completely consumed and then kind of just the irradiated zombie-like husk left close to its star. Happy Halloween, everybody. Next, let's talk about TRES 2b, the darkest world. Oh, you can't see it. Here, let me enhance. So this is the darkest known planet. So it reflects, we think, about 0.04% of the light that hits it. No one will ever be as goth as this planet is. It is incredibly dark, way darker than coal or black paint. It is a massive planet, a bit larger and heavier than Jupiter, orbiting very close to its planet star, just 3% of the distance Earth is from the sun. So it is scorching hot, pitch black, and right on top of its star. We're not sure why it's so dark. It could be the presence of vaporized sodium, potassium, and titanium in its atmosphere, but until we're able to study it more closely, we won't quite know. But it is mysterious and just the stuff of sci-fi nightmares. So getting to friendlier territory, let's talk about Kepler 90. So this is a star system with 8 planets, much like our own, ranging from some relatively friendly super-Earth planets to a couple of giant planets in the outer system. The difference being Kepler 90's planets are very close to their star. So they are, here's the orbits of Mercury, Venus, and Earth for comparison's sake. All of the planets in the Kepler 90 system are within Earth's orbit. So imagine the stargazing you'd be able to do on Kepler 90H, just seeing that many crescent planets in the night sky. Pretty remarkable. And then finally, I'd like to close with talking about Proxima Centauri b, our nearest planetary neighbor outside the solar system. So a mere 4.2 light years away. Hop, skip, and a jump as far as the galaxy is concerned, but still 25 trillion with a T miles from here. This is a rocky planet, just a touch larger than Earth, located well within the habitable zone of Proxima Centauri. So this is the sci-fi dream, right? Our nearest star with a rocky world that could support life, theoretically, if all other things are perfect. Now, there are some problems with this. It's really close to that star. So while the temperatures ought to be right, it orbits Proxima Centauri b every 11.2 Earth days. So that's how long its year is. It whizzes around that sun pretty quickly. As a result, even though the temperature range ought to be good because Proxima Centauri is a dim red star, there's a lot of solar wind pressure. So unless this planet has a very powerful magnetic field, its atmosphere has probably been stripped, and with it, any liquid water. Still, it's pretty awesome that there is a rocky planet in the adjacent star. And what that tells us is that planets like Earth may not be that uncommon. But, of course, the search continues. So with that, I would like to open to any questions the audience may have. And yeah, happy to chat. Thank you.